In purple.
Okay. Yeah, so thanks for coming, and it's a huge pleasure to have Chandra Chekuri give a talk on Densest Subgraph. I'm sure you guys will all love it. Yeah,
thanks, Eric. It's great to be back right in the building. Many years, but thanks for coming. So this talk is on Densest Subgraph, right? Let me start with the definition of the problem that we're interested in. So we're given a graph, undirected graph, and you want to find some dense subgraph, right? And most of the talk will be on this notion of density, which is just for a given set of vertices, how many edges are there in the subgraph induced by the set divided by the size of the set. So that's the density of a set, and you want to maximize this for all subsets of the vertex set, right? So we'll call lambda star, right? And just a silly example, right? If you have a graph like this, there's a clique in there of size 4, and that turns out to be the densest in this particular case. The density is 6/4. So you want to find that, right? And why is it interesting? Well, people like to find various kinds of dense subgraphs for various applications, right? There are many papers on this. I'm not coming at it from an applied angle. But I just want to point out for some reasons that I'll mention shortly, that people study these various notions of density, as many of you know, in social networks and community detection and stuff. And there's an industry on there, both for both practical reasons and theoretical reasons, right? And it's also technically interesting from an algorithmic point of view. And just very recently, for instance, there's various new versions, like there's a paper by Austin Benson, who used to be here in Kleinberg and Welt, on some variation where they changed the density to some pth power and so on, right? So there are new variations that come up. So in general, we were interested in density where there's some function on the set of vertices S, and you want to find the densest subset, right? And what classes of F are interesting and what are tractable, right? Something we want to play with. And one reason I think densest subgraph is popular is because it's actually polynomial time solvable, right? And it's a classical result. It's a very nice combinatorial optimization exercise or connection that you can solve this in polynomial time. And I guess it goes back to the work. The original reduction is to flow. Then you can see, as we'll see shortly, a reduction to a more general problem with submodular function minimization. And then Moses in 2000 came up with a nice LP relaxation, which will play an important role in this talk. Okay, so he's not here, sadly, but we'll see where. And Ashish also has a nice paper I'll mention as we go along. Okay, so one of the reasons I got interested in this is because of the connection to submodular functions and supermodular functions. So let me just briefly define it for those of you who may not be familiar. That a real valued set function is submodular if it satisfies this inequality for all sets A and B. F of A plus F of B is greater than or equal to F of A union B plus F A intersection B. Equivalently, the marginal value of an element V to a set A is larger if it is compared to another set B, right, which includes A.
Minus
So,
signs?
Sorry.
Should there?
Yeah. This I thought I fixed this, but I didn't. Okay. Yeah, it should be minus. Yeah, sorry. So F of A plus V minus F of A is the marginal value of V to A. It's bigger than F of B plus V minus F of B, whenever A is a subset of B. Right? This is a diminishing marginal returns. Many of you know it. And supermodular function is the opposite of that, right? F is supermodular if and only if minus F is submodular. Another way of saying it, let's look at this marginal value definition. That I'll use this notation: F, the marginal value of V to B, is bigger when B is bigger, right? That is supermodular. Submodular is less, and supermodular is bigger, right? Okay. So let's look at the special case of graphs, right? And many of us know that the cut function of the graph is submodular. If you look at a graph and look at a set of vertices and define F of S to be the number of edges leaving that set, that is submodular and non-negative. But I'm interested in the other function. If you look at the set of vertices S and look at the number of edges inside E of S, then that is supermodular. Okay. And it's easy to see, right? Because E of S is half of the sum of the degrees minus the cut. Right? The number inside is the degrees minus what's leaving divided by half. Yeah. And so this is modular, this is submodular, so this is supermodular. But it's also monotone, which this is not. Yeah. Okay. Okay, that's good. And so now instead of looking at the densest subgraph problem as a graph problem, we can lift it to the supermodular setting, right? I give an arbitrary supermodular function on some ground set V, and you want to maximize f of s divided by s. Okay, and clearly graph case is a special case when f of s is E of s, right? And this is tractable, and it's nice to see it this way, right? Can we solve this? Well, you guess lambda, and then you say, is there a set such that f of s, the ratio of f of s, the cardinality of s is at least lambda? You look at this, you check that this is possible if and only if the minimum of this function is less than or equal to 0. And this is a submodular function, so you can do submodular function minimization in polynomial terms, so you can answer this question. That's one easy way of remembering why densest subgraph is solvable in polynomial, right? Okay, and it's a supermodular function maximization. Okay, all right. So there, why did I get interested in this problem? It's actually really because I saw an archive paper with a nice conjecture, and I got attracted by the conjecture. Right, we'll come to that. But there are other reasons, technical reasons also, because there's a lot of work in recent years somehow, right, for whatever reason, right, on fast approximate algorithms for very large graphs, right? And one of the problems people have thought about, in fact, Moses' 20-year-old paper was motivated by these fast algorithms as opposed to reduction to flow, which is kind of slow, right? And then people come up with variations, like I mentioned, like the recent paper, the papers on streaming, parallel, dynamic, you name it, right? In many communities, right? So there's a lot of work on this topic. And in particular, some of the things I will talk about are connected to this conjecture that this group of people, Georgia Tech, made on a very simple iterative greedy algorithm that seemed intuitive, but was hard to analyze, right? So that was the main reason I got interested in this topic. And then there's some connections to supermodularity and LP relaxations and stuff. So we'll hopefully see some of that in the talk. Okay, so what are the new results we get in this paper, right? One of the things we did was you can get a 1 minus epsilon approximation to the densest subgraph problem using some, I think, interesting connection to flow. I mean, the flow-based algorithm which runs in 1 over epsilon times m polylog n. Okay. So here the improvement is from epsilon square to epsilon. Now with the new near linear term Maxwell algorithm, this may not be as compelling from a theoretical point of view, because you can get, I think, log 1 over epsilon in some sense, right? The flow. I don't know if people will implement that algorithm, but this one is very eminently implementable. And then we'll answer this conjecture that I'll mention, and then some connections to supermodular functions that we'll see. There are some other results too, which are, I think, interesting, but I don't have time to actually explain what they are, so I will skip that, right? And overall, and there are many nice simple connections. There's nothing very, I think, complicated, but still, hopefully, the results are interesting. Okay, so the rest of the talk, I'll start with this nice LP relaxation that Moses described like 20 years ago, and using that, we'll analyze a couple of algorithms. Okay. Okay. So what did Moses do, right? He wrote this LP relaxation for densest subgraph, right? So let's look at that. So we want to maximize E of S divided by S, right? So it's a ratio problem. Whenever you have ratio problem, you want to normalize the denominator to 1 if you want to get an LP, right? So, and then sort of keep the objective somehow in the numerator. So integrally, we want to know, have a variable ZV, whether it's in the set or not. And for every edge, we want to know whether it took that edge or not, right? So you want to maximize how many we take, subject to taking 1 unit of the vertex, right? If you want to normalize it. So the sum of the ZV becomes 1 because you are trying to normalize it. So when can you get an edge UV? You can get an edge UV if and only if you take both its endpoints in the set. No? So how do you express it in a linear form? You write it as min of ZU ZV. Yeah. So that's it. XUV is less than or equal to min of ZU ZV. It's not linear, but you can write it as XUV is less than or equal to ZU, and that's Moses LP. I mean, it's not difficult to write this LP, but I think the reason he wrote it is he wanted to analyze some greedy algorithm, and then he showed that this is actually an optimal LP for densest subgraph. This is another proof that you can solve densest subgraph in polynomial time, right? Which is different from the flow reduction and different from.
In what sense is it optimal?
Sorry?
In what sense?
The optimal value is the density, optimal density, and you can also recover the. You can round it to. I mean, you can round it to optimal system. Yeah. Okay. So. Okay, let's write the dual of this because the dual has some nice structure, and the dual is like some kind of a mixed packing and covering LP, and it has a nice interpretation. So instead of just staring at it, let me show you the dual in a slightly different way. Okay. So the dual is trying to do the following, right? What is it trying to do? Think of the edges of the graph as one side of a bipartite graph, and the vertices on the other side. Okay. Every edge has to be assigned to one of its endpoints. Okay. Fractionally, you don't have to assign it integrally, right? Every edge in the graph has to be assigned to either U or V. Okay. And you want to minimize the maximum load that any vertex gives. Okay. So the dual is saying assign the edges of the graph to the vertices or orient the edges fractionally to either endpoint. Okay. So that no vertex gets very highly loaded, right? And so the minimum overall orientations, fractional orientations of the load on the vertex, maximum load on the vertex is the dual. Okay. So if you write it as an LP, what does it say, right? There are variables which say YUV, comma U, comma V, right? You can only assign to these two endpoints. So this is saying YUV U plus YUV V is greater than or equal to 1. So every edge has to be assigned to one of its two endpoints. And the total load on any vertex has to be at most D, and you minimize D. Yeah. That's a dual. If you look at Moses LP and write it, that's what you get. Okay. And you can see the dual looks like a flow problem, right? Because like an assignment problem or a flow problem. Yeah. Okay. This dual, even though it's a very simple, so from this immediately you can see that you can solve the dual by max flow and guessing of the dual optimum value. Yeah. Because you want to find, you can check feasibility of the assignment by solving a flow for a given value of lambda, right? It's just a flow assignment problem. And so you want to minimize the lambda for which the flow is feasible. Right. And so this is another reduction to flow, but it's a little bit actually nicer and cleaner reduction to flow than the original classical reduction. Even though this is also very simple, somehow this came later. Yeah. Okay. So why are we also again interested in this? The dual, is a kind of a mixed packing and covering LP, right? It has assignment greater than or equal to 1 constraints and less than or equal to D constraints. So it's what's called a mixed packing and covering LP, right? And people study these approximation algorithms. How fast can you solve mixed packing and covering LPs, right? And I mean, Ashish had a nice paper in 2014 where he showed that Bhamani and Munagala that you can actually, I mean, if you use multiplicative weight updates based methods, you will get m polylog n over epsilon square sequentially, but they also had a parallel algorithm. That was the more interesting thing, and it's a clever idea of width reduction, which is cute. I won't have time to explain it, but so you can do that, right? You can apply multiplicative weight updates sequentially. This is not that difficult. Parallel is more tricky. The open question in this area of mixed packing and covering in general is, can you get a single epsilon dependence on the running time as opposed to epsilon square? It is known for pure packing and pure covering LPs, but this is a mixed packing and covering LP. It has greater than or equal to and less than or equal to constraints. So it's still open, and it's a nice open problem. Can we get something which is near linear in the number of non-zeros in the matrix and only 1 over epsilon dependence on the error, the multiplicative error? So this is an open problem. So, but this is not any arbitrary mixed packing in LP, right? It's some particular mixed packing in covering LP. So it's not clear why you cannot solve this particular LP fast, right? So you can ask, and people tried doing that. And so this Wu, Savali, and Wang using some machinery, connects of the machinery, they got something like that, where they had extra maximum degree term. Okay. I'm not telling you their result in the generality, but if you apply it to densest subgraph, you can get M, delta, polylog, and or epsilon. Okay. So, what we can get is that we can get for densest subgraph M, polylog, and or epsilon, right? And so for the special case, we can get this fast algorithm. And I guess maybe more interesting thing I would like to mention is how we did it, right? It's not based on solving the LP, but looking at this flow graph, right? And saying, okay, what is the natural reduction to flow, right? You guess lambda and you try to solve max flow in this, right? Okay, if you have an exact algorithm for max flow, okay, that's great, right? That's a separate issue. If you have a really fast algorithm like we do now in theory, then it's good, right? But the result we prove is that you can run an approximate max flow on this, and you still get 1 minus epsilon approximation, right? So more precisely, what we prove is that you run the augmenting path algorithm, right? And if the augmenting paths are not, if the augmenting paths, you need to run the algorithm only till the length of the shortest augmenting path is log n or epsilon. Okay, and then you will get a 1 minus epsilon approximation. Okay, so this is kind of like if some of you may know the matching result, right? In maximum cardinality matching, if you want a 1 minus epsilon approximation, it suffices to make sure that there is no augmenting path in the residual graph which is longer than 1 over epsilon. Okay, then you will be 1 minus epsilon approximation to max flow, to matching. This is saying for the densest subgraph, it is sufficient to ensure that the augmenting path length is greater than log n over epsilon. At that point, you're good, right? So you don't have to run the flow algorithm too long. You'll be good if you stop at log n or epsilon, right? So the number of iterations of blocking flow or whatever you need to do is only log n or epsilon. So structurally, it's a nice result, even though it also implies a running time. Yeah. Okay, so that's the. I just want to mention this result that you can run flow for a few iterations and it will give you a good approximation. Okay, so it's not based on LP directly, it's based on flow. And even though the flow this network is coming from the LP. Yeah, so that's one result, right? We hadn't seen this kind of application before, so I thought it was nice. So it gives some other application, but I will skip that. Okay, the rest of the talk I want to talk about a greedy algorithm, right? And the conjecture that motivated me to even look at this problem first, right? And hopefully that will also be interesting to you. So I guess Moses' initial motivation to study this problem was some greedy algorithm that some people propose, which is very natural in retrospect, right? To solve the densest subgraph problem. And what is that algorithm, right? It's very simple. You start with the smallest degree vertex, remove it, right? And you keep doing that, right? So you look at the smallest degree vertex, remove it, then put the next smallest degree vertex in the residual graph, put it, right? So you get an ordering of the vertices, okay? And then after you create this ordering, look at all the suffixes of the ordering, right? And among all the suffixes of the ordering, pick the one which has the largest density. Yeah, simple algorithm, right? Okay. So, and Moses showed that it's a half approximation. Okay, via the LP, he showed that it's a simple heuristic gives a half approximation. Okay, so here is an example, right? Just because I'm going to come back to it again. So you have a just also to show that the half analysis is tight. So here is a graph. Yeah, it consists of a bunch of disjoint cliques and one big bipartite clique. Okay, so there are there's some degree parameter d. So this say d equal to 3 here. So there are 4 cliques, and then this is KDD. There are lots of vertices here and 3 vertices on this side. Yeah. Okay. So what is the densest subgraph here in this graph?
the clique.
No, it's not the clique. Yeah. So this is the densest subgraph. Why? Because the average degree in this is everybody. I mean, this is huge, no? So everybody has roughly degree D. Okay. So let's compute this. No, it's D times D is the number of edges divided by D plus D. No, it's, I mean, when capital D is much bigger than thing, and it's roughly D. Well, a clique only gives you D over 2, roughly, right? So you take this. Yeah, so that's all. Okay, but what does the greedy algorithm do, right? The greedy algorithm, let's see, let's run it, right? It'll peel off. I mean, it looks at the smallest degree vertex, right? What is the smallest degree vertex? Well, it's I'll break ties to make my life a little simpler, not because right. So it'll peel off these red vertices initially because they're all 3. Everybody here is 3, right? Degree 3. But it'll peel off these red vertices first, yeah. And then it'll start peeling some yellow vertices. Don't worry about them. And then it'll peel off the clique vertices, yeah. That makes sense? Okay. But now if you look at the suffixes have to include all the cliques, no? And the cliques have density only D over 2, so you're being forced to go towards D over 2 while you have to only take this guy. Okay. Okay, so you get half. But that's the worst case. That's right. Okay. Okay. Okay, now one of the questions we asked ourselves, because a lot of papers on peeling, because as soon as the algorithm is so simple, no? So it's easy to implement. And so a lot of people in applied areas found this very appealing because the simple algorithm, it gives a good approximation guarantee. In practice, it works very well or something they say, right? And so there are a lot of papers saying, apply peeling to this, apply peeling to that, right? This measure, that measure, and all that stuff. But they all have their own analysis, right? And so one of the things I was trying to understand was, okay, is there a reason why this peeling algorithm is working in general? Is there an analysis that works for all supermodular functions, right? And turns out that you can define a simple greedy algorithm for any supermodular function. So what is that? What is the notion of picking the smallest degree vertex, right? Now what is the notion of degree, right? You look at the vertex now with the least margin value with respect to V minus V. Okay. If the first vertex first element you take off is the one which minimizes f v to v minus v, right? Which is the degree in the case of a graph. But if a supermodular function, this is what you should do. Okay, this is the natural generalization of peeling to an arbitrary supermodular function, right? And you get again, you can ask, does it algorithm work well? Does it have any provable guarantees, and how does it behave, right? Okay, and it turns out that you can prove this theorem, right? And what is the, you should suspect that it can't be great for all supermodular functions, right? Maybe or maybe it's good, right? How do we know? So what we show is that you can define a simple parameter of a supermodular function. And the approximation ratio of this greedy can be characterized by that parameter. Okay, so what is that parameter? Yeah, so the parameter is this quantity, right? I'll write it down here again, right? Okay, this measures something like, for some of you are familiar with something which is like curvature, or there are some various ways of saying how close this function is to some other class of function. This saying, look at f of s. F of s is the value of the entire set S, right? Compare it to the marginal values of each element in the set, f of v s minus v, right? Okay, and take this ratio. This gives you some, by supermodularity, this is at least as big as f of s. Okay. And so this gives some number with respect to S, and you maximize this over all sets S. So what is the worst case in this function, right? So that is some something you can associate with the function. Let's call it CF. Yeah. So theorem is that greedy gives you 1 over CF approximation for supermodular. It's a very simple analysis. I'm not going to do it, but it's not hard, right? So identifying this parameter was the main thing. We looked at the analysis and said, this is what happens, right? So what is CF? Let's understand it. Instead of trying to prove this, let's understand what CF is telling us for different special cases. Yeah, a little bit. Okay. Let's see what it is for a graph. What is this definition for a graph, right? If I have a graph, what is CF? Look at any set of vertices, right? What is f of s? The number of edges in it, right? What is f vs minus v? But if you look at vertex, what is it contributing to the rest of the graph? It's degree inside that graph. Yeah. So the numerator is the sum of the degrees. The denominator is the number of edges. That ratio is 2 for any set, no? In a graph. Yeah. So for a graph, CF is 2. So you're getting half approximation for greedy. No? So that's it. So what this is saying is that for a graph, CF is 2, so you're getting half approximation. For a hypergraph, for instance, with rank R, CF is R, and you get 1 over R approximation. You look at other functions, you'll get whatever CF is, right? You can evaluate it. For example, I said this Benson, Kleinberg, and Weld paper. Recently, they wrote a paper where they said, "Oh, you should do this." I mean, they had various heuristic reasons to consider this function, right? They said raised to the power of p, that is a function. And then they said, oh, appealing gives you p plus 1, right? But if you analyze the CF, you'll get p plus 1, right? And it's also supermodular for p greater than or equal to 1, right? So it's a unified analysis of peeling, right? As a function of as some simple way of characterizing the performance. Yeah. Okay. So that was good. But
question.
yeah.
Sorry, this is probably a stupid question, but I didn't get like how when you have f instead of degree, like what's the objective function? Like so before it was like edges over the size.
No, it is just max f of s over s. Yeah. Yeah, and this is f of s, so I'll just see the special case. Right? Yeah. That answer it?
Yeah.
Yeah. Okay. All right. So that's. I want to the proof. Proof is very simple actually. Just putting 2 and 2 together once you know what you're looking for. Right. The rest of the talk I want to talk about the paper which really motivated us to look at this problem is that we saw that greedy gives you only half approximation. Right. So can we improve that half using a simple algorithm that is also like peeling but does something more, right? By iterating it multiple times. So this group, I guess there's a lot of authors, I wrote them down in the previous slide, Goob et al, right? Came up with a very simple heuristic which is motivated by multiplicative weight updates on the dual and the greedy algorithm. And they made this conjecture that it will converge to a 1 minus epsilon approximation in some number of iterations. Yeah. So let me tell you what that algorithm is, and then we'll discuss what. Right? Okay. So the algorithm is as follows, right? It's a kind of it runs this peeling algorithm many times. Okay. Each time choosing the vertices in a slightly different way, right? Okay, so there's a motivation for it, but let's first understand the algorithm, right? So what is the first iteration? The first iteration is the basic greedy algorithm, right? You peel the vertices in degree, you remove the lowest degree vertex, then you remove the lowest degree vertex in the graph and so on, right? Okay, at the end of the first iteration, you look at the load on the vertex, where is the number of its degree at the time it was peeled, okay? So think of when I peel the vertex, I assign all the edges to this vertex, right? So the lowest degree vertex, when you peel it, all the edges incident to it give it the load corresponding degree. When I peel the next vertex, the current set of edges get assigned to it. That's its load. Yeah. So the first iteration is clear, right? Yeah. But we keep track of this load. In the second iteration, you look at load plus degree. Okay. And then you peel in that order. So, and then again, you update the loads based on how many edges get assigned. Yeah. So, okay, let me run an example. Yeah.
So is the argument there like just over the degrees and then plus the previous load, or is it like the argument of degree plus load?
Oh, its argument is a degree plus load. Sorry, it should be this. Yeah. Yeah, thanks. Yeah. Yeah, it's the min of the degree plus load. Yeah. So the previous iteration is influencing the next iteration on who gets peeled first, right? Okay, let me run an example, right? Remember this example. Okay, let it refresh. Okay. Okay. So what did the algorithm do? It put in the first iteration, put all the red vertices first, right? Because their degree is 3. Okay. But after the first iteration, let's look at the loads, right? So when I peel this, its load is 3, no? Because I assigned these 3 edges to it. So when I peel this again, all of this get load 3. Yeah. And these vertices get 2, 1, 0. Don't worry about the yellow vertices, they're kind of noise, right? Okay. And what about the clique vertices? The first vertex of the clique gets load 3 because its degree is 3 when it's peeled. No? And the second vertex gets load 2, and the third vertex gets load 1, and the last vertex gets load 0. So you get this, right? Okay, so that's what this first iteration, I'm just putting them in order. But in the second iteration, what does the algorithm do? Now the load of this vertex, right, is 3 plus 3, right? Load plus degree is 6. Yeah. But well, this vertex load is 0 and its degree is 3. So this vertex gets picked first in the next iteration. Yeah. So you see in the next iteration itself, the clique vertices get peeled away first. Okay, and then it gives you the optimal solution in the second iteration. Right? Okay, so if you take the suffixes, so it will give you the optimal solution in the second iteration. Yeah. Because this is their algorithm. Do it many times, and each time take the suffixes then, right?
But then the 3 nodes won't they be at the end still?
No, which one? This one?
Yeah.
No, because once I remove this, its degree also is falling, no? Right? It's a the load is 3, but by the time it's peeled, its degree is 0, it's become 3. I mean, yeah. There is some tie breaking, but don't worry. Yeah.
So you're choosing, like you're updating it's not like you put them in order and then you go in order, you are ordering them by their load and then.
No, the ordering of the load, the peeling is based on load plus degree.
But it's degree before the iteration started or degree updating as you go?
A degree updating as you go. Yes. So even the original greedy algorithm is degree at the moment you peel it. Right. So that remains the same, except that the load is static from the previous iteration. And then your loads accumulate over time. Yeah? Is the algorithm clear?
Wait, what do you mean by accumulate?
Okay.
Remember
The next, okay. This one, in the third iteration, the load for this vertices is now added based on this second iteration. So in this case, it's just 2 iterations. If you want to do third iteration, the load will be the previous load plus this.
How do you decide when to have the iteration?
Yeah. So that is the conjecture. Okay. The conjecture was that if you do this algorithm after 1 minus epsilon, you will get a 1 minus epsilon approximation after O of 1 over epsilons per iteration. That's their conjecture. Yeah. So a very simple algorithm, right? And very natural. I mean, I don't know if it's natural, but very simple for sure, right? And they implemented it. It was there in some, I think, dub paper, I think. Right? And it works very fast. I actually downloaded the code, and they hyper optimized it. You can see they didn't want to use priority queues. They use some array data structures. And you take on the old laptop, it will run like a huge graph, right? Sometimes hard to imagine in like few seconds or something. Right? You can see how fast it's running, right? And it seems. But anyway, so they made this conjecture. But the thing is, it was tricky to analyze this because they couldn't prove that it's even better than half, even after a lot of iterations. Right? So it's kind of like they made this. They have a very nice heuristic. It seems to work well, but why does it even converge? Forget how many times. Right? It was not clear. Okay, so anyway, so I mean, they got this algorithm based on some multiplicative weight update insight. They say it right themselves, but somehow it was hard to put 2 and 2 together to figure out why this is working, right? And I don't think we have a correct answer for what is happening in this algorithm in particular, right? Let me tell you what we proved. We proved that it converges, right? And I said, it converges to 1 minus epsilon approximation in 1 over epsilon square times some bigger factor, right? It depends on the log n and also the maximum degree by optimum value, right? So I think I don't have I have the statement somewhere here. I think let me go back to the theorem statement, right? Okay, we'll come to this. Don't worry. It will converge in not exactly in what they claim, that they didn't have any dependence on anything else, no, just epsilon. But we don't get this. We get 1 over epsilon square times something, right? Which depends on the graph and other thing, right? But what we also were able to prove is that it's not a graph result. It works for every supermodular function. Okay, so it's not particular to graphs. So I will come to that, right? But how did we prove it, right? I think that's, to me, is more interesting than just the result, right? Our first observation was, he looked at Moses LP. It's very nice LP, right? But it's sort of like, if you like submodularity like I do, and I like to see, is it a theorem about graphs or is it a theorem about supermodular functions or submodular functions? Just a natural question, right? The same thing when I look at an LP like this, I sometimes like to think, what if it was a supermodular function? What would I do, right? It turns out I wrote it intentionally that way. I just rewrite this LP not as a linear program, but as a concave program, right? So really, if you put, you remove the variables XUV from the LP, if you want just ZVs, right? There are no edges, then this is how it will look, right? But now you have this nonlinear term, but it's a concave function, right? And you say, look, why is this a concave function, right? Well, and so you can solve that too. It turns out this is just nothing but basically some Lova's extension of the corresponding supermodular function, which is the edge set of the graph. Okay, so let me briefly discuss some connections there, and then I'll come back to this LP, right? So many of you may be familiar, but there is a way to take real valued set functions and extend it to the cube, right, to the continuous domain. There are many ways of doing it, and in the context of submodularity, Lova's define this extension, right? And what is Lova's extension of a function? It doesn't have to be submodular. You have to tell me, for a given, I have a ground set V, right, 1 to n, say, and I give you now, it's a set function, right? For any set, I have a value, but I want to extend it to the continuous domain 0, 1 to the V, right? So how do you extend it? One way of extending it is, defining it is, the value at a fractional vector x in the cube is, you pick a theta between 0 and 1 and look at all the elements which are bigger than theta and take the expectation of f of x. Okay. So let me write it down in an example, right? Suppose I have a 3-element set, and I want to assign a value to this fractional vector. Okay, so one way of defining it, the Lova's extension is you pick a theta at random, okay, between 0 and 1, and look at all the elements which have the fractional value greater than theta, and look at f of that set, and take the expectation of the randomness of theta. Right? I can write it an explicit formula, but I hope the details don't matter. It is some way of extending a nice way of extending the set function to the cube, right? Okay, and what happens if you have the case of E of S, right? If E of S is your function for a graph, right, then this is the Lova's extension. Yeah, so it turns, it's not a coincidence that this is right. No. So if okay, so what am I saying? Maybe I'm not being very clear. Suppose f of s is defined as the number of edges inside the set of vertices defined by s, right? then I can ask what is the lowest extension of this. Then it turns out it is sum over all edges in the graph, min of xu xv. It's very simple to calculate and see this. Okay, don't worry. If you've seen it, you see it. Otherwise, it's just some way of extending. Right? Yeah.
What is this extension usually used for? Why is it defined?
Oh, because it's only defined in the corners of the cube, right? The set function is saying, the set function is defined only, you can think of it as defined in 0, 1 to the v. And then we want to extend it to the continuous space. It's called continuous extension. There are ways, you see, how do you interpolate inside the cube from the corners? There are many ways of doing it, and this is one way of doing it. Okay, so what do we know about the lowest extension? Why is it famous? Because he showed that lowest extension is convex if and only if f is submodular. And it is concave if and only if f is supermodular because of the negation, right? Yeah. Okay, so it's nice, right? And what is nice is that there's always a convex extension, but the nice thing about lowest extension is it's easy to evaluate it, no? Given x and a value are equal to f, you can evaluate the lowest extension. While it's not true for a canonical way of extending and getting a convex function. Right? So anyway, that's why it's. So whenever you want to optimize with submodular function, you should use a continuous extension, right? At least try it. If it works, it works. If it doesn't, okay, fine, right? So if you want to lift from densest subgraph to this more general problem, suppose I want to solve this maximize f of s over s where f is supermod. Okay, and how would you write a LP relaxation for it, right? Like Moses wrote for densest subgraph. I claim, in fact, you will write like this. Yeah, what will you want to do? You will again normalize the denominator to 1, but now you don't have edges to rely on, right? You just have like a function, right? So you have to extend the function to the reals, right? Well, pick your favorite extension, right? But it has to be tractable. Well, in the case of maximization, you want concavity, right? To be tractable. You use lowest extension. Remember, it's supermodular, so it's concave. Submodular is convex, supermodular is concave. So this is what you would write, and then say, hope for the best, right? It turns out that this is actually exact, just like what Moses did. You can think of it as rounding according to what the lowest extension is telling you to do. It's very simple once you know the tools, that this is actually an exact relaxation for this problem for any supermodular function. Yeah. Okay. So that was the long ago observation I made. Oh, that's nice. But the thing is, what perspective does this give you, right? To solve the conjecture. That's more, right? Okay. Okay. So once you have this, right, you can ask a more general question, because just like we had a greedy algorithm works for any supermodular function to give you some ratio, no? It is something which depends on the function. It need not be half, it can be worse than half, but it's something depending on the function. So you can define a iterative greedy algorithm also for supermodular functions. It's a very simple natural extension of the iterative greedy algorithm for just maintain loads and right, and you can ask, is a conjecture true for arbitrary supermodular functions, or is it only true for graphs, right? So in fact, we prove that you can prove a theorem which says it converges in 1 over epsilon square times something, some factor, for any supermodular function. So right, there's a nice simple greedy plus extension of supermodular functions, and the iterative algorithm converges. Yeah, that's the theorem, right? In fact, the reason I would say we are not looking to extend it to the supermodular functions for the sake of it. The proof came about because we are looking at this more general class. Okay, so I don't know how much time I have. Let me I can't sketch. I'll just hint at what the proof looks like, because it's a bit messy. Lambda is the optimum value. So, you see, this term is not very nice, no? It's not strongly polynomial in general. It can be quite large, or it can be small depending on your instance, right? But we can't prove only dependence on a 1 epsilon. We have all these extra terms. We don't know whether it's necessary. We don't have a tight analysis for the algorithm. Actually, we don't know. I'll come to the open problem at the end. This is what we are able to prove. Okay, so a few words on a little bit on how we proved it. Okay, the way we proved it is by we wrote a different LP. Okay, Now it's an LP, right? Remember, we started out with this concave program based on the Lovaas extension, and we couldn't see how to connect this greedy algorithm with this concave program. We somehow thought it should be possible to do it, and so we went kind of a detour, and the detour is based on a different extension of submodular functions, and a connection between Lovaas extension and that extension, which I'll call the Edmonds extension, right? Because it really comes from the Edmonds theory, right? Okay. So take any supermodular function F, right? Now consider all permutations of this vertices, right? That's an exponential number of permutations, right? So for a given permutation or an ordering, you can define a vector, right? And this is intimately connected to the Lovaas extension, but I will I'll tell you only at high level details. So for a given ordering of the vertex set, you can define a vector, right? What is the coordinates of the vector, right? So let's look at say a 4-element set v1, v2, v3, v4. Yeah. Now consider this ordering sigma, which is v2, v4, v3, v1. Yeah, that's one ordering. Then what is the coordinate, the third coordinate of that vector? It is f of v2, v4, v3 minus f of v2, v4. Right, look at the position of v3. It's the marginal value of v3 to the ones which come before it. Okay, so that defines for this ordering, a vector. Okay, okay, okay. So from the theory of submodular functions, one can show that the Lovaas extension value can be rewritten in a different way, which is the minimum over all orderings of the ground set, right? So I want to know what is the Lovaas extension at a fractional vector x. It is the minimum over all orderings of the ground set, the inner product of x and the vector q sigma. Okay, it's a rewriting of the Lovaas extension. You need to know a little bit of submodularity theory to make sense of this. Okay, so the reason why we are going towards this alternate definition of extension is, remember, greedy. What is the greedy algorithm? No, it is producing some ordering, right? Yeah, every iteration is producing an ordering, right? So how do you make sense of orderings? Right, orderings are somehow intimately connected to the definition of the Lovaas. So we are groping to find how we can use orderings as a first-class object in the analysis, right? Because the entire greedy algorithms is producing a lot of orderings, right? At the end of the algorithm, what do you have? You have a lot of orderings, and one of those orderings is good, right? So you need some analysis idea to know where orderings are coming from. Okay. And it's not obvious from this relaxation, right? This looks very compact, but it's concave, but it's not helping us, right? So what we did with this connection is we started out with this, right? We know this is good. Then we transformed it where, we for reasons you will see very simply, instead of making this max in the objective, we made this as a constraint and minimized this constraint. I just flipped the ratio. Instead of maximizing f of s over s, I'm saying minimize s over f of s. If you do that, you'll get this program, right? So you say, okay, what did you do? Nothing interesting, right? But if you do this, you can use the Edmonds extension to rewrite this as a linear program. Okay, we went from a concave program here. We wanted a linear program. Okay, but the linear program now has an exponential number of constraints, one for each ordering, because of this. This is greater than equal to, and this is a minimization, so you can write this as a linear program. Okay, and we know we like linear programs a little better, and then we took the dual. Okay, so I mean, I'm just telling you how we came to it. I'm not saying this is the most straightforward way, right? It is so at the end of the transformation, we get a linear program. Okay, what is this linear program? Let me just spend a little bit of time. It has one variable for each ordering of the ground set. Okay, so it's a huge number of variables, right? So you want to maximize that. Okay, there's some subject to some packing constraints, right, which involve these orderings. Okay. Okay, so one can show by these transformations that this is exact relaxation for densest subgraph because the original one was an exact relaxation of densest subgraph. Okay. Now, once you have this in this particular form, you can say, okay, look, this huge beast of a linear program at least has the structure that you're playing with orderings. And greedy algorithm is producing a lot of orderings, right? So there must be some connection to what it is doing and some LP which has orderings in it, right? Even though it seems superficial, that's how we are groping it, right? And I mean, what do you do, right? You have to do it. And it turns out that once you have this LP, you can say, maybe I can solve this LP using multiplicative weight updates, right? Because it's a huge exponential size LP, because it's some structure, and you can, right? You can show that there's a very simple greedy iterative algorithm based on multiplicative weight updates, which solves this LP and will give you convergence to optimum in some number of iterations, right? But that's what we did. And then, but greedy plus plus is not doing multiplicative weight updates directly with respect to this LP. Okay. So the technical step, which is again maybe not too hard in retrospect, which I'll skip this, is that we are able to show that greedy plus plus with the right setting of parameters is an approximate implementation of multiplicative weight updates with respect to that LP. Okay, so it's not an exact implementation of multiplicative weight updates with respect to that LP. So remember, the first iteration is not quite well defined with respect to the multiplicative weight updates. The first iteration is somehow magical, right? Because it already gives a good approximation. It's not clear why that, right? So that took us some time, but the end of the story is that we have this LP, which is an exact relaxation for densest supermodular set problem. And we can show that the supermodular, the super greedy plus plus is essentially, I mean, approximately solving this via multiplicative weight updates. Okay. So then based on that and this connection, we are able to prove that it actually will converge to the output. Okay. So that's it. That's all we could do, right? It doesn't mean that our analysis actually is the right one for this particular algorithm. Okay. So we are able to prove convergence in dependence of 1 over epsilon square via this indirect route, right? And so it does converge, right? You know, which is, and the dependence on epsilon is not worse than the original conjecture, but there are additional terms we are able to, right? So hopefully, I mean, you know, even if you don't care about this problem, the thing which the tools are like, I think playing with these extensions, continuous extensions of submodular functions is good. And sometimes you have to lift from the graph problem to the higher level to see the structure, right? This ordering structure would not have been apparent unless we went to the supermodular setting, right? You know, why should you care about orderings? The orderings are very natural in the world of submodular functions. They're not so natural just if you look at graphs. Well, they're much more natural in they're actually fundamental objects in the submodular setting, right? So when we saw that, you know, we made the connection more easy. Yeah. Okay. So that's the result. And there's some, it's a little bit messy to actually formalize all this, but I'll stop with some open problems. You know, even though we are able to prove convergence, we don't know of any example where the algorithm takes more than omega 1 over epsilon iterations. Okay, we can prove, I mean, it's not hard to construct in instances where you need 1 over epsilon iterations to get 1 minus epsilon. We don't have any example where it takes more than 1 over epsilon iterations on graphs. So I don't know what the right answer is, right? In the sense of, for this particular greedy plus plus algorithm, we don't know the right answer. We don't, yeah.
Why do you think the practical paper conjectured 1 over epsilon squared?
Because it seemed like multiplicative weight updates, right? So, and that's the right answer for multiplicative weight updates, right? So I don't know, I mean, so we also thought, okay, there must be a very easy connection to multiplicative weight updates now. When you see 1 over epsilon square, I say, okay, fine. It wasn't so easy to prove it. So, yeah, but in fact, it's not clear that it's actually doing multiplicative weight updates only, right? It may be doing something else, right? Our proof is not quite what I would call the right answer for this problem, even though we're proving convergence, right? And is there dependence on any other parameters necessary? For example, the original conjecture said only 1 over epsilon square, right? While our dependence has like a lot of factors which are not maybe necessary.
The theorem was only for graphs for densest subgraph.
Yes.
The convergence is that the fact that convergence is true in general.
Yes. Yeah. Now, in fact, even for so one could potentially conjecture, no, that yeah, it is not clear even for arbitrary supermodular functions. I would be, if you can prove a lower bound for a general supermodular function that you cannot, it won't converge in 1 over epsilon square iteration, that also will be interesting. That you need extra parameters, right? I mean, it seems a little strong to say for any supermodular function, it should not depend at all on anything else other than epsilon, right? But each iteration is pretty complicated, no? So it's not obvious that it should take more. So I mean, I didn't think too much about general supermodular functions and lower bounds. Even for graphs, I thought we should prove it. We couldn't prove tightness. Okay. Okay. And I know there are other problems on densest subgraph. A lot of some questions on parallel algorithms, dynamic algorithms. There are some nice papers but I find this more compelling, at least from a technical point of view. Right. Okay. Happy to answer questions. Yeah.
Is there a reason to use like iterative fitting over multiplicative weight updates? Like why prove that it's just instead of just?
I guess that's the difference between theory people and non-theory people, right? is that in the sense if you implement this algorithm, because first iteration is already so good, well, the first iteration of multiplicative weight updates will do nothing interesting, right? Because it will just say pick any ordering. You shouldn't pick any ordering, right? Because already the first iteration is in practical examples is 0.8 or 0.9, right? So this algorithm is even after a few iterations is crazily good, right? So people, right? While we wouldn't care so much if you prove a theory result, while if in practice, I think they would very much prefer an algorithm that is very good even in the first few iterations, right? So I think it was motivated by the fact that even in one iteration it's doing a very good job. So how can we improve it? No, so while multiplicative weight updates won't do that. First iteration is junk, right? It says take any order.
Actually implemented multiplicative weight updates.
Yeah.
This problem. It's terrible. It's just exactly one over epsilon. Every parameter in multiplicative weight analysis, you actually get the worst case when you implement it. There's no.
Yeah, it's not a, yeah.
Goes better in practice, and that one is you see exactly what you.
I also not for this problem. Yeah, in fact,
For this specific.
No, for this specific problem, I also have another project where we implement it. It's not good. The greedy plus is so good. So we implemented we implemented a parallel version of multiplicative weight updates in a huge cluster. Okay, because I was doing some parallel. The sequential version is faster than that because it takes. It takes 10 iterations to get very good, right? 10 sequential iterations are better than the multiplicative updates theoretical log n or epsilon square. Because in multiplicative weight updates, the epsilon is baked into the step size. You can't go faster if you want a probable guarantee, right? But then it slows you down considerably while this one, it doesn't care, it's a heuristic. Right?
Then even if you at least for a series, you relax the guarantee. If you relax the guarantee, you don't make the results.
Yeah, so in a way, I think it's some of these results and papers, it's a learning experience, right? Until you implement or you see the drastic difference in the performance between multiplicative updates or some other algorithm and a heuristic which is also well motivated, you don't see the difference. You're saying, they're all the same. Right? Anyway, yeah. Yeah, even the flow algorithm, I think, so even though we proved a nice theory result on the flow algorithm, I'm sure when you put the data structures for blocking flows, nobody will find it any faster than this algorithm, right? Once you put data structures, like it becomes pretty slow also. Right? Flow data structures are nice in theory, but pretty slow.
So with the flow thing, can you get exact
Oh yeah, flow. I mean, you can do the flow. I mean, the flow. Sorry, the flow reduction is I mean, you do binary search for lambda. So now that becomes not strongly polynomial, right? But that's okay, right? You know, you have to do binary search for lambda, and then the optimum lambda for which the flow exists. The minimum lambda for which the flow exists is the exact value for the lambda star, right? But then you have to do binary search for that lambda. Or you can use parametric search. Okay, fine, they're all both good, but you get strongly polynomial time, but it's going to be very slow, right? Yeah. Anyway, I mean, these are all really don't need exact answer for this densest subgraph, right? It's just a proxy for something else. Yeah, for me, the nice thing is that it works for any supermodular function. I think that's a nice result, right? A simple iterative algorithm, well motivated. First iteration has a good guarantee, and it will converge eventually. So you have a good heuristic that for any supermodular function, which is nice.
Can you also can you reprove Charikars like that the first iteration does well, or somehow this is only about once you have the first iteration?
No. Charikar's thing is that's easy. I mean, in fact, we proved, right? You know, we proved a more general result. That 1 over CF approximation holds for one iteration.
Oh, okay. Oh, right.
Yeah, that's for one iteration, right? For graphs, it's 2, a half, and so for any supermodular function, one iteration gives you 1 over CF approximation. Yeah.
So there's this lower bound of omega 1 over epsilon for how long it takes to converge.
Right.
But if I want to know, like, how bad could the 5th iteration be? Like, how does that function change as the number of iterations increases? In the worst case.
So then you're asking
So the first iteration gets a factor 2 approximation. What's the best what's the worst of the second iteration?
Open question. Good thing you asked me. so we could not prove, and they could not prove also, that after 2 iterations you're strictly better than half. You see, it may look like an innocuous question, right? They could not even prove that it converges. No, there is the reason they're smart people. It's not like they didn't try, right? It seems strange that when I saw the conjecture that, okay, look, you're claiming that it will converge in this iteration rate, right? But how come that you can't prove that it converges in even after infinite number of iterations?
So it doesn't necessarily get like gradually better, or they just know.
No. Multiplicative weight update algorithms don't get gradually better necessarily. The monotonous, it doesn't, because they're working in the dual, they don't always work monotonically better. But for this algorithm, it is possible to conjecture that after 2 iterations, it is strictly better than half. But I don't know whether it's true or not.
If you make in the counter example, it gives you 1/2 for the one iteration. If it makes the small tweaks up just a little bit bigger, there's still only about half dense, right? And then one vertex that still has a high degree. You're going to keep it.
Okay. So now, I mean, okay. So we do know omega 1 over epsilon lower bound, right? But so in some sense.
But after 2 iterations.
2 iterations is probably not strictly better than half, right? But your question is, see, it's connected to whether you need extra parameters suppose I can prove it is it converges to 1 minus epsilon approximation in 2 over epsilon square iterations, right? Then you have a nice thing. But because we have all these like silly terms which you don't know whether are needed or not, it's hard to argue in 5 iterations what happens. Other than so maybe in 2 iterations it doesn't do. But well, it's a good question. In 10 iterations, can you prove it is better than half, right?
So if IVR was right, if you make the click D to be 10, then you think in 10 iterations you still get 1/2. Like the small D parameter, like look like.
Okay, let's see. I mean, I'm not seeing the details. Maybe I can. So you take the click and you say what? You make it.
Like if the small D is big, then it seems like after that small D thing, you don't seem to get.
I'm not saying it, but okay, maybe you can stop the recording. If you find anything, let me know. We did spend some time, but not.